Okay, today we finished our discussion of drag force. We actually started and finished the discussion of the total drag force, where the total drag force is defined as the area integral of p cosine theta plus the area integral of tau sine theta. The flat plate boundary layer discussion focused on tau, so really now what we're doing is we're adding the pressure contribution. To understand where that arises from, we can think of flow encountering a cylinder or a sphere in which the leading edge of the flow might look like a rotational flow, but then we have a separation zone on the trailing edge for a wake. And that wake structure has low pressure and it's uniform pressure throughout. So that creates a net pressure difference between the leading and trailing edges, so that the integration then of the pressure over the area is not zero. The integration of p cosine theta is not zero. So that's how we can sort of formally go through the definition of the drag force. But the way we usually approach it for real shapes is empirically based on a drag coefficient, 1/2 rho times u0 squared, where u0 is the approach velocity, times AP, where AP is the projected area. That is the area that is seen by the approaching flow. So it's the frontal area of the object. Now the drag coefficient, CD, is usually a function of the object's shape and the Reynolds number of the flow. An example of how CD varies with Reynolds number is for the case of a sphere, which is figure 9.21 in the text, has a region that drops off inversely with Reynolds number, and then another transition that occurs at higher Reynolds number. So in this early region, CD is approximately, or is actually equal to 20, let me write that again. So in this region, it's 24 over the Reynolds number, and then the transition that occurs up here is around 500,000. And that represents the point at which the boundary layer on the surface of our object transitions from laminar to turbulent, and that creates this hiccup in CD. So this is a turbulent boundary layer. Over here we have a laminar boundary layer, but it still has a wake structure as shown in the sketch in the top right. So anytime we're above a Reynolds number of about 100, we get to this wake region. That wake region then manifests itself in drag coefficients that have these different structures depending on if the boundary layer is laminar or if the boundary layer transitions to turbulent. In the low Reynolds number limit, shown here with the 24 over RE, it's actually the shear stress that dominates, and that allows for a theoretical solution. So this is an example for the case of spheres. For other shapes, there's going to be different curves. Various references in the text are going to point you towards values of the drag coefficient for particular shapes and particular Reynolds numbers, which you can then use in calculations of force balances using this empirical approach.